Assalamualaikum warahmatullahi taala wabarakatuh, and a very good morning to everyone. So this is the third video for course Advanced Thermodynamics MME6154. I am your lecturer, first lecturer, Dr. Izatul. Okay, as for course content, previously we have learned chapter 1, Introduction of Thermodynamics, that consists of two videos, part 1 and part 2. So in this video, we will continue on chapter 2, energy, energy transfer, and general energy analysis. In this chapter, I will introduce the concept of energy and define its various forms. We will discuss the nature of internal energy, define the concept of heat and the terminology associated with energy transfer by heat. We also will discuss the three mechanisms of heat transfer, which are conduction, convection, and radiation. The concept of work will be defined, including electrical work and several forms of mechanical work. I will also introduce again the first law of thermodynamics, energy balances, and mechanisms of energy transfer to or from a system. We will determine that a fluid flowing across a control surface of a control volume carries energy across the control surface in addition to any energy transfer across the control surface that may be in the form of heat and or work. Energy conversion efficiencies also will be defined in this chapter. And lastly, we will discuss together the implications of energy conversion on the environment. Now, let's start with the introduction. If we take the entire room, including the air and the refrigerator or fan, as the system, which we already learned in chapter 1, the definition of system and types of system in thermodynamics, which is an adiabatic closed system. Since the room is well sealed and well insulated, the only energy interaction involved is the electrical energy crossing the system boundary and entering the room. As a result of the conversion of electric energy consumed by the device to heat, the room temperature will rise. For example, we have here a refrigerator operating with its door open in a well-sealed and well-insulated room, or a fan running in a well-sealed and well-insulated room will raise the temperature of air in the room. Now, let's see some of the forms of energy. Energy can exist in numerous forms such as thermal, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear, and their sum constitutes the total energy E of a system. Thermodynamics deals only with the change of the total energy. We have here macroscopic forms of energy and also microscopic forms of energy. What's the difference between these two? For macroscopic, those a system possesses as a whole with respect to some outside reference frame, such as kinetic and potential energies. However, for microscopic forms of energy, it is those related to the molecular structure of a system and the degree of the molecular activity. Now, let's see the internal energy, okay, denoted with capital U, the sum of all the microscopic forms of energy. So, please remember, for internal energy is actually equal to the sum of all microscopic forms of energy. Then we have a familiar energy, types of energy here, which are kinetic energy and potential energy. In kinetic energy, the energy that a system possesses as a result of its motion relative to some reference frame, while in potential energy, the energy that a system possesses as a result of its elevation in a gravitational field. For example, this car. Okay, the macroscopic energy of an object changes with velocity and elevation. Here I summarize some of the equations that you will learn in thermodynamics. Okay, we have kinetic energy per unit mass. Please take note, okay, capital and small letter for per unit mass. And then we have potential energy per unit mass. Okay, mass flow rate equation, energy flow rate equation, total energy of a system, okay, U plus kinetic energy plus potential energy. And then we have energy of a system per unit mass. Okay, it's basically is the same thing. Okay, and then total energy per unit mass. You can learn this more, okay, by reading the textbook of thermodynamics. Alright, now some physical insight to internal energy. What is sensible energy, latent energy, chemical energy, and nuclear energy? These four types of energies definition will be explained after this. Okay, for sensible energy, it is actually the portion of the internal energy of a system associated with the kinetic energies of the molecules. For latent energy, it is the internal energy associated with the phase of a system. Chemical energy, the internal energy associated with the atomic bonds in a molecule. While nuclear energy is the tremendous amount of energy associated with the strong bonds with the nucleus of the atom itself. For thermal, it is equal to the sensible plus latent, but for internal, it is sensible, latent, chemical, and nuclear. So as you can see in this figure here, various forms of microscopic energies that make up sensible energy. And then the internal energy of a system is the sum of all forms of the microscopic energies. The total energy of a system can be contained or stored in a system and thus can be viewed as the static forms of energy. The forms of energy not stored in a system can be viewed as dynamic forms of energy or energy interaction. Okay, I believe most of you already learned this kind of terms before. The dynamic forms of energy are recognized at the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. The only two forms of energy interactions associated with a closed system are heat transfer and work. The difference between heat transfer and work is an energy interaction is heat transfer if its driving force is a temperature difference. Otherwise, it is work. Now, let's see a little bit on nuclear energy. Okay, you can read this more in thermodynamics textbook. But nuclear energy by fusion is released when two small nuclei combine into a larger one. Okay, this is basically the definition of the nuclear energy, how it is created. Okay, the uncontrolled fusion reaction was achieved in the early 1950s, but all the efforts since then to achieve controlled fusion by massive lasers, powerful magnetic fields, and electric currents to generate power have failed. Okay, so this is a little bit on nuclear energy. Okay, then this is the important part, which is mechanical energy. Okay, what is mechanical energy? Okay, mechanical energy is the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. Okay, kinetic and potential energies are the familiar forms of mechanical energy. Here we can see the equation of mechanical energy of a flowing fluid per unit mass and also rate of mechanical energy of a flowing fluid. Okay, mechanical energy change of a fluid during incompressible flow per unit mass is as below. Okay, this is the equation for mechanical energy change of a fluid during incompressible flow. Okay, I believe all of you already learned during your degree what is the definition of incompressible flow. Alright, rate of mechanical energy change of a fluid during incompressible flow is as below. Alright, some applications of mechanical energy. Mechanical energy is a useful concept for flows that do not involve significant heat transfer or energy conversion, such as the flow of gasoline from an underground tank into a car. Okay, mechanical energy is illustrated by an ideal hydraulic turbine coupled with an ideal generator. Okay, turbine and generator. In the absence of irreversible losses, the maximum produced power is proportional to A. The change in water surface elevation from the upstream to the downstream reservoir, or B. The drop in water pressure from just upstream to just downstream of the turbine. Now, let's move on to energy transfer by heat. Actually, we have learned the first law of thermodynamics in chapter 1, which is energy cannot be created nor destroyed. It can only change form. Let's see this figure of a soda. Okay. A can of cold soda left on a table eventually warms up when a body is left in a medium that is at a different temperature. Energy transfer in the form of heat, okay, higher temperature body to lower, takes place between the body and the surrounding medium until thermal equilibrium is established. Okay, body temperature equal to the medium temperature. Energy can cross the boundary of a closed system in two distinct forms. Energy, which is heat, and also work. During an interaction between a system and its surrounding, the amount of energy gained by the system must be exactly equal to the amount of energy lost by the surroundings. Remember, it cannot be created nor destroyed, it only can change form. Alright, let's see this equation. The change in internal energy of a system is equal to the heat added to the system minus the work done by the system. Okay, change in internal energy is actually equal to heat added to the system minus work done by the system. Alright, what is heat transfer? The definition of heat transfer is the form of energy that is transferred between two systems or a system and its surrounding by virtue of a temperature difference. Heat is energy transition. It is recognized only as crosses the boundary of a system. A process during which there is no heat transfer is called an adiabatic process. Okay, in adiabatic process, the system is well insulated so that only negligible amount of heat can pass through the boundary, and then both the system and the surroundings are at the same temperature. Thus, no driving force or temperature difference for heat transfer. Let's see this figure. Temperature difference is the driving force for heat transfer. The larger the temperature difference, the higher is the rate of heat transfer. Okay, now let's see several equations for energy transfer by heat. Okay, equation for energy transfer, heat transfer per unit mass, okay, denotes with small letter q equal to uppercase Q over M. Okay, don't forget the unit SI, kilojoule per kilogram. And then amount of heat transfer when heat transfer rate changes with time. Then here Q dot equal to heat transfer rate. Okay, heat transfer rate. and times with dt, integration of between T1 and T2. Okay, the symbol is Q, uppercase Q, unit is kilojoule. And then heat transfer rate Q equal to Q dot delta T. Please remember that energy is recognized as heat transfer only if it crosses the system boundary. And I already explained this before in chapter 1. During an adiabatic process, a system exchanges no heat with its surrounding if it is in adiabatic process. Now, let's see several heat transfer mechanisms. Okay, we have conduction process, convection process, and also radiation process. Okay, what is conduction? Conduction is the transfer of energy from the more energetic particles of a substance to the adjacent less energetic ones as a result of interaction between particles. And here we have the equation for conduction process. The second one is convection, the transfer of energy between a solid surface and the adjacent fluid that is in motion, and it involves the combined effects of conduction and fluid motion. Okay, here we have the convection equation. All equations are in red. Okay, red types. Okay, Q dot convection equal to HA. H is equal to the convection of heat transfer coefficient. And then we have radiation, the transfer of energy due to the emissions of electromagnetic waves or photons. And here we have the equation. Okay, sigma here is the Stefan Boltzmann constant equal to 5.67 times 10 times the power of negative 8. Okay, and the lambda here is emissivity of the surface. Alright, now let's see the energy transfer by work. Okay, just now we see energy transfer by heat. Okay, so heat equal to work, and energy interaction between a system and its surrounding, where energy can cross the boundary of a closed system in the form of heat or work. Okay, what is the definition of work? Work equal to the energy transfer associated with a force acting through a distance or any energy interaction that is not caused by a temperature difference between the system and its surrounding. So it's a little bit different with heat just now that we see the definition of heat. Okay. For example, we have a rising piston, a rotating shaft, and an electric wire crossing the system boundaries are all associated with work interactions. Unit of work is energy units, which is kilojoule. Okay. Work done per unit mass of a system is denoted by small w equal to uppercase W over M. Okay, remember anything that you per unit mass, the symbol is small letter. Okay, work done per unit time is called power, W dot, with units kilojoule per second or kilowatt. Formal sign convention, heat transfer to a system and work done by a system are positive. Heat transfer from a system and work done on a system are negative. Okay, a little bit more explanation on energy transfer by work. Okay, both are recognized at the boundaries of a system as they cross the boundaries. That is, both heat and work are boundary phenomena. Okay, system possess energy but not heat or work. Both are associated with a process, not a state. Unlike properties, heat or work has no meaning at a state. Both are path functions, i.e., their magnitudes depend on the path followed during a process as well as the end states. Okay, so here properties are point functions, have exact differentials. We have here dv equal to v2 minus v1 equal to delta v. Path functions have inexact differentials. Okay, so we have here the integration of w equal to w1 2, process 1 2. Okay, from state 1 to state 2. Okay, in this figure shows that properties are point functions, but heat and work are path functions. Their magnitudes depend on the path on the past follow.